All right, so for this example of a really big binomial, we're going to roll 120 dice, which you should be doing in class. We're going to count up how many sixes you roll, and that's our variable x, and we're looking for the probability that we get 25 or more successes, and a success is rolling a 6. So this is a binomial, and to calculate that, we'll do 1 minus binomial CDF. Binomial CDF with 120, 1/6, and 24, this is 24 or fewer sixes, and if you do 1 minus that, you get 25 or greater. So if I type that in my calculator, 1 minus, remember, we're working with normal CDF, which is up at the top of that menu. Binomial CDF is down toward the bottom of that menu. 120, 1/6. Just type it in as 1/6. If you round that off to 0.167 or something, you're just rounding it. You're making it a little bit wrong. So just put the fraction in. Calculator's good for that. And I want to do a 24. 1 minus that gives me 0.136. So I'm calling that the true answer because this topic is called normal approximation of binomials. And we're going to come up with an approximation in just a minute that hopefully is really close to that one. But overall, the goal is to realize that if we try something and succeed or fail every time, that ultimately we can use a normal curve to estimate pretty accurately the probability of falling in a certain area on that normal curve. So let's talk about how we can estimate that exact answer, that true answer. If we were to graph this thing, let's talk about the shape, center, and spread of this particular binomial distribution. So most of your notes were about the fact that this thing takes a certain shape under certain conditions. What is that shape? What is our current topic? Normal, bell curve. It will be normally shaped. Right, we talked about how if the probability on a binomial is less than 0.5 or greater than 0.5, that creates a skew. But if you have enough trials, it will actually kind of morph into a normal shape, which is what makes it the normal approximation. Under what conditions will it be approximately normal? When it's big. What makes it big? How many?
When NP is greater than 10 and the square root of NPQ is greater than 10.
Just NP and NQ.
Oh.
You're ahead of us. If we have enough trials combined with a probability of success that makes us expect at least 10 successes and failures. I should put the word both there. Sorry, that's kind of out of order, but you get the idea. If we are doing an experiment, we are trying enough times. Now, if it's really, really hard to succeed, you might need a really, really big bunch of trials. If there's only a 1 out of 100 chance of success, then you're going to need at least 1,000 trials. If it's 50-50, you only need 20 trials, right? Because if it's 50-50 and you try 20, you should see 10 and 10 on average. But if it's, the further your success gets away from 0.5, the more trials you're going to have to happen for this to be what we expect. So we are rolling 120 dice. 1/6 of the time should be a 6. So how many successes and failures do we expect? What's 1/6 of 120? So our dice are normal. Our distribution of number of sixes is normal because we have an expected successes of 20 and an expected failures of 100. Okay, so where is this thing centered? Now, we've known the center, the mean of a binomial distribution for a while now. If it's binomial, mu sub x, that's the average value. Where would this distribution of number of sixes rolled be centered? Or what's the expected value? That's what we just talked about, right? N times P is the expected value or mean of a binomial. We are rolling 120 dice, 1/6. So our mean, our expected value, the center of our normal curve is at 20, which is on the graph you see in class, should be clustered around 20. How about the spread? All right, sigma sub x. X is our variable. This is the standard deviation of this distribution. What's that formula you said a minute ago, Lindsay? Square root of NPQ. Okay, so for this particular one, it's a square root of 120 trials times 1/6 probability of success times 5 out of 6 probability of failure, which is 4.08. Okay, so if this binomial, which just so we're all clear, this thing we're doing, this approximation we're doing, is so you can understand greater concepts to come very soon. But we wouldn't really need to do this if we really wanted to answer this question, because we already found the true answer right there in green, right? So this is out of date because of binomial CDF on your calculator. If you didn't have binomial CDF on your calculator, even if you had binomial PDF, you would still have to do that for 25 and 26 and 27 all the way up through 120, and you wouldn't want to do that. But having CDF really makes this obsolete. So just realize this is a concept, but not something you would want to do to answer this actual question. Okay, so let's use the approximation. This approximation, this is an approximately normal curve. You know it's not perfect because the histogram of number of sixes rolled would be like a jagged histogram, not a smooth curve because it's discrete. But we're approximating it with this. It should be centered at 20. This would be 24.08, and this would be 28.16, just adding 4.08 with each step. And the question is, what's the probability that we get 25 or more? That's going to be in this area right here. That red area is our normal approximation of that true answer from above, 0.136. So let's find that red area. Now we're back to our current topic. Our current topic is normal CDF, basically. So on this normal curve, which is centered at 20, what's the probability that I go 25 to infinity on a curve centered at 20 with a standard deviation of 4.08? Okay, so in my calculator, that gives me 0.11019. Let's call it 1102. 1102. So it's pretty close. Our normal approximation of 0.136, 13.6%, was about 11%. So it wasn't too bad, but it's clearly an approximation. All right, this is not a perfect normal curve. We didn't have the perfect standard deviation. It's off by about 2.5%. So it's not great. Could anybody remind me what the continuity correction is, or how we could get a little bit better there? If we are estimating, let's zoom in here. What we just added up, or what we're trying to add up, is a bunch of individual bars. And what we did with a normal curve was we went from 25, and when we did our normal area, which was something like this, we went from 25 to infinity. But in reality, this bar, because it's discrete, stretches from 24.5 to 25.5. So we should be able to get a little bit closer to the reality by changing this to 24.5. So let me retype that and see what I get. If you change that 25 to a 24.5, then you change this 1102 to 0.135. And it was supposed to be 136. So it got real close if you did that correction. It's still not going to be perfect. Remember, if you look at this enlarged diagram, we're still going to miss. It's kind of like an integral in calculus. You're using rectangles to sum up a smooth curve with a Riemann sum. Well, in this case, we're using a smooth curve to estimate the rectangles, kind of backwards from calculus. But we got really close because if a binomial is big enough, then it takes on the characteristics of a normal curve. Okay, so let's agree on this fact, even though this is obsolete. This is the takeaway from this. A big binomial is basically a normal curve if in P and in Q are both at least 10. That much is very important, even if finding a probability for an actual binomial can be done with your calculator rather than this estimation.